the um, lecture 7. This is the second part of lecture 7. So one thing to note is that the shearing of the plate or the sheet starts from the creating the, so the punch will impact the sheet and it will start creating a crack on the both the top and bottom edges of the sheet at um, at in this case this is 7.4. So at A and B it will start forming the crack. Okay, and then it will have to go through and it will have to, those points A and B have to meet in order for the shearing to be complete. Okay, so typically what happens is that you might have a rough fracture surface. So if you like to have that, like to have a smooth surface that will nicely shear off and create a clean edge, um, it needs to be done at a very fast rate. So the smooth edge is called the burnished surface. So that one, so you can see this one. So you have some smooth surface and also very rough surface. Okay, so you're going to have some small area that is smooth and some area that is not that smooth. And if you need really smooth surface, then it means that the sheet metal has to be very ductile, and it will actually decrease with sheet thickness and clearance. So suppose the thicker the sheet, the rougher the edges will be, and the more ductile the material, the smoother the surface will be. But what happens is that if you have a very brittle or highly cold work material, then that punch needs to travel very little in order to complete the shearing. So in this figure you can see the deformation zone where you have very high shear strains. And the width of that zone depends upon the rate of shearing and the punch or the punch speed. And if you have increasing punch speed, then if you have very fast punch speed, then the heat generated by the plastic deformation is confined to a very narrow zone. And so then so the faster you punch, the smoother the sheared surface. And what is the punch force that is required is given by, it's called F max. If you see equation 7.4, you can calculate the maximum punch force, and so it is 0.7 times S underscore, S subscript UT, which is the ultimate tensile strength of the sheet metal. T is the thickness, and L is the total length of the sheared edge. So if you have a round hole of diameter D, L is equal to pi times D. So from that you can calculate the maximum punch force. So there is an example here, example 7.1. You please take a look at that, how it is done. So we will have some example problems to be done along the same lines. Okay. So what are the different types of shearing operations that you can have? You can have die cutting, you can have fine blanking. So in so the first one is um, punching, and the second one is blanking. So if you have punching, then that means the piece that is removed from this area is discarded, and if it is blanking, this the material that comes out is the, so if you need this as the final part, then the outer piece is discarded. Okay, so whatever is so if it is punching, the material that is punched out is discarded. If it is blanking, that means the material other than the blank is discarded. So uh, in that also there are common shearing operations called die cutting and fine blanking. And this is the um, so the typical conventional blanking and the fine blanking. So fine blanking is on the right side, and the this one is the typical conventional blanking. And depends upon the, so that will get you the right kind of um, dimensions and shapes that you want. The other types of um, parameters that come into play are, like, it's called, one is called slitting. So if you have a circular pair of circular blades, so it will go either in a straight line or a circular or a curved path. So if you are cutting a white sheet, then it is called straight. I mean, so it is just like, taking a um, pair of scissors and cutting through a cloth. Okay, so that is called slitting. Then you can also have, so suppose you have a thermoplastic material or a very plastic sheet, then you might take a sheet of or a steel rule, so that can be blanked into various shapes using steel rule dies. Um, so it's a hardened steel blade that is bent to the shape to be sheared like a cookie cutter. Okay, typically like a cookie cutter. So and then you might have some kind of a die that is pressed against the material, so that so you have some kind of a support in order to get the material out. There is also something called nibbling. So those are all the different variations of the process. Okay, then one thing to note is that there is quite a bit of scrap in the shearing operations. So it can be as much as 30% of the original sheet for large pieces, and so you have to make sure that the scrap is minimized as much as possible in order to minimize the cost of the manufacturing process itself. So so this one describes the type of shearing dies. So you have uh, punch dies and I don't see this one in the textbook. Um, okay, yeah, I see this one. Okay. Um, yes. So this one shows the different kinds of dyes and things like that that is used for making um, different kinds of uh, materials. Okay. So what kind of die shapes can you have? So you can, I mean, so why do you have these kinds of different types of dies? Depends upon the type of blank or type of um punching that you have to do in order to make the final shape. So these also can affect the amount of noise that is produced during the manufacturing process. Okay, so different applications to that. That's all. Okay, so the different kinds of dyes are um, so these are the different punch and die shapes, as I said. And then the other things that you can we talk about is also the different aspects is like you can have what is called a compound die. So you are not going to have one single die or one single stroke material to create that. So it is not a simple punch and die process. So you have to do it um, in multiple steps. And they are slow, and these dies are also pretty expensive for individual shearing operations. Then you can also have what is called a progressive die. So if you have a multiple operation like punching, bending, blanking, etc. at very high production rates, then you can use what is called a progressive die. Okay, so you do one operation, then the part is moved to the next die, and so on. Automatically moved. Um, you can also have, so in order to do that, you can have, suppose your operation takes place at different stations, multiple stations, um, which is arranged in a straight line or a circular path, or I mean, it is somehow transferred from one step to the other. um, it can it may need to do that. Okay, so those are all the different aspects um, of the tool and die operation, different operations on that. Suppose you have um, if you want to cut sheet metal, there are several methods for cutting sheets and dies. So the first one would be bandsaw, obviously. So I think it is explained in one of the future in the next chapter, I believe. Okay, so it's done in multiple steps. Um, so it's cut using a bandsaw. Then you can also have flame cutting, like you're using an oxyacetylene torch. Um, you cut that, like if you're doing shipbuilding or very heavy construction operations. So you may use some kind of a flame cutting operation. Then you can also have what is called friction sawing. You use a disc or blade, or the other one that is very commonly used, especially for composites and things like that, is called water jet cutting or abrasive water jet cutting. uh, so those are used for both for metals as well as for non-metallic materials. Then the more common one nowadays is called laser beam cutting. It is very consistent cutting operations using CNC controlled equipments. Okay. So these are, suppose you want very consistent operations and consistent dimensions, then you may use what is called laser beam cutting. So they use this process of uh, you blank them, you laser cut them, and then you laser weld them, and then you stamp them into the shape and form that you want. So this is very commonly used in the automotive industry. So especially for high productivity type of operation, this is used. So this is again another example of that. So it's a side rail and shock absorber component, fender. So none of these are made in one piece. So they cut them, weld them together, join them, and then stamp them into the shape and form that you want. So it's done in multiple steps. So one thing to note is that many of these sheet metals have to be bent into the shape that you want. So what do you have to be worried about? You have to be worried about what is the maximum thickness that you can take and bend into the bend radius. Suppose you have a large bend radius. I mean, it may not be possible to bend this thickness into the shape and form that you want. Suppose you have a 3-inch thick piece of metal. Can you bend it into, say, 90-degree bend? You cannot do that. So everything has to be controlled, and that is given by this equation in section 7.4. So the approximate bend allowance is equal to alpha times R plus KT. I don't know if it is given here or not. I think you should be able to see that in the equation there. I mean, so this is above this figure, you should be able to see that equation. In practice, the value K ranges from 0.332 for what is R? R is the bend radius, and T is the thickness of your sheet. And so there are some rules of thumb for the thickness that you can have. So minimum bend radii for various materials at room temperatures is given here. So if you have a very hard aluminum alloy, the minimum is 60 and so on. So you can control that, and you can get the approximate numbers for these materials. Okay, so that is given by that formula for bend allowance. So if you look at equation 7.5, that should give you the strains at the outer and inner fibers. So outer fiber is the outer edge, what is the strain, and the inner edge is um, the strain on the inside. So typically the strains in the outer and inner fibers are equal in magnitude and are given by that equation 7.5. So here again you can, how much you are reducing the thickness. So you have um, some kind of a rough uh, correlation between the two, where the bend radius over thickness um, is given by 60 over r minus 1, where what is small r, um, if you look at that, you should be able to see that alpha is a bend angle. Um, you have to check what is r. I cannot find that, I'm sorry. Should be able to see that, okay? Please look for that, what is small r, and figure that out. Now, one thing to note is that when you bend something, um, there is going to be some kind of a distortion. So the outer and inner strains are different, and that difference will increase with the ratio of the radius over thickness. So the higher the thickness, more will be the distortion. Okay. So there are some equations here. Please take a look at that. So so it should um, I mean, I'm looking for that. What is the, yeah, R is a percent reduction of area of the sheet in a tension test. So you should be able to calculate what is the true strain, and from that you should be able to calculate. You should be able to incorporate the bend radius and the thickness, etc., into that equation. So the true strain is related to the radius and the thickness. So you should be able to calculate those things. So um, so the minimum uh, radius over thickness, minimum bend radius over thickness is equal to 50 over r minus 1. So that is what is uh, plotted here in this. Here it is 60 over r minus 1, but typically they have calculated minimum r over t equal to 50 over r minus 1, and the experimental data that is a better fit is 60 over r minus 1. So that's where that 60 over r minus 1 is. Okay, so if you know the reduction in area, which is this is r, so if you know the r, and if you know the bend radius over the thickness, r over t, you should be able to calculate those things and plot that and use it to have some kind of a general idea of what is allowable and what is not. Okay, so let me stop here, and this will be um, the file 7B. Okay,